Today is chapter 5, Minerals and Rocks. Usually, in studying geology, people usually start with minerals and rocks. In our case, we are taking it in chapter 5. Why? Because for us as engineers, the definition of minerals and rocks and how to differentiate between different minerals and different rocks is not the target of our study. The target of our study is the properties of the rocks. Rocks and soil. If I am an engineer and you tell me that beneath your building you have a soil or a rock, and this rock has the following properties, this is very enough for me. You will just tell me what will this rock behave in the future. That's all. But I don't care if this rock was created 10 million years ago or 1 million years ago. For me, it's the past is not that important. What is important is the present properties and the future properties. And future for me is not another million years. No, future for me is the lifespan of the building. It may be 100 years. That's all. So this is what I care for in studying any material. So just a reminder, chapter 5 now is minerals and rocks, chapter 4 geologic structures, chapter 3 plate tectonics, and chapter 2 was introduction to engineering geology. Of course, we took chapter 1, which was introduction to geotechnical engineering. But now we are going to go deeper into minerals and rocks. Just a reminder from the previous lecture, where can we find minerals and rocks? Of course, if this is our Earth, as we said, the crust is divided into hydrosphere, lithosphere. What is a hydrosphere? Everything related to water. Lithosphere is everything related to solid. So if I'm looking for minerals and rocks, I'm not going to find it in the hydrosphere. It will be in the lithosphere. So first I will go to the lithosphere. A reminder, what is the relation between the lithosphere and everything? This figure is very, very good. This is the lithosphere, everything related to solids. It's the land. Hydrosphere, everything related to water. Atmosphere, everything related to air. Then we have biosphere. It takes from the three. It's anything from these three related to biology, living organism. So any living organism in the lithosphere, the hydrosphere, the atmosphere are called biosphere. So this figure, I advise you to add it to your lists, because it helps you to gather all the information in one shot. So we are going to study the lithosphere. What are we going to study in this lithosphere? We are going to study minerals, rocks, and if I'm going to study rocks, it means that as a geotechnical engineer, I should study soil, because these usually in my design as an engineer, I care for rocks and soil. I never see minerals. Minerals is the base, but I never see it. I just care for rocks and soil. So this is exactly what is in the lithosphere: soil, rocks, and minerals. Let's discuss the definition. Minerals, naturally occurring inorganic substances. So minerals are naturally. It cannot be anything man-made. You cannot just make chemical reaction and produce a new material. No, mineral should be naturally occurring. And it is inorganic. It cannot be something containing organic matter. Rocks made up of several minerals and organic substances. So rocks is minerals, 1 or 2 or 3 minerals combined together, and it may contain also some organic substances. So here minerals, no organic. If I add group of minerals together, it will be rock. If I add group of minerals plus inorganic, it will also be rock. What about soil? Soil is a mixture of decomposed organic matter and disintegrated rocks and minerals. So soil is the disintegration of these two. If minerals disintegrate, they will be soil. If rocks disintegrate, they will be soil. So soil is the remaining part of the disintegration of these two. Some basic definitions. This is a definition for minerals, this is the definition for rock. But before we go to minerals and rocks, let's go a step behind. Element. You remember the periodic table? The periodic table is the table of elements. So elements are the smallest form of matter that cannot be broken down further by heating, cooling, or chemical reaction. So this is the base. So the base is elements. If elements combine together, they form mineral. So mineral naturally, as we said before, we said that mineral is naturally occurring inorganic substance. So this is the definition. Naturally occurring solids consisting of one or more elements in specific properties, or proportions, not specific proportion. So a combination of elements give me a mineral. What is rock? We said before, rock, naturally occurring solid composed of one or more minerals. But it may contain also inorganic substance, as we said before. Here, rocks, it may contain, in addition to these minerals bound together, it may contain some inorganic matter. Organic matter. And these are examples of these rocks. Let's go to the properties. Just imagine that all of these terms you were supposed to know and understand. If I'm speaking about properties of minerals, as we said now, minerals is for us, it's the smallest. Of course, there is element which is smaller, but we don't see elements. We don't see elements for us in our work. I'm not going to see to deal with oxygen alone, carbon dioxide alone, no, or carbon alone, no. I deal with the combination of these in the form of mineral or in the form of a rock. So if I take minerals which is smaller than the rock, it's the main constituent of the rock. What are the properties? If I know the properties of minerals, then I can define the properties of rock and the properties of soils, of course. So what are the properties of minerals? Properties are divided into physical and optical. For physical, plots, color, luster, streak, hardness, cleavage, fracture, tenacity, structure, specific gravity, plots. And then optical, light, reflection, lots of items. Then this deals with the crystalline form of the matter, the crystals itself, how it is formed, the shape, and so on. some descriptive study. In the descriptive study, they gather minerals together in groups. They say that all of these minerals have something in common. So we call it, say, the silicate group, because they all have silicate mineral in them. Then there is feldspar group, and so on. So carbonate minerals and so on. Actually, all of this is very good, but this is good for geologists. We are, as I said at the beginning, we are geotechnical engineers, or at least engineers, civil engineers, any type of engineer, even architects. I don't care exactly for lots of these properties. For me, it is not that important. It is important for geologists. So now we are going to study from all of these just few properties that are important for us. What are these properties? Of course, as an engineer, do you think what properties affects us? Is it the shape, the color, or the strength properties? Is it the shape, the properties? Is it the shape, the color, or the strength? Which is important for us as engineers? Strength, of course, because I use this material to build buildings on top of it. If I build a building on top of a red stone, is it different from building it on top of a yellow stone? I don't care. But if I put it on top of a soft stone or solid stone or medium stone, this is important for me. So what I need is something related to strength. Sometime I will show you something that is related to visual inspection, but it is important for me. Also, it will relate to another strength property. The first property is hardness. Let's check where is hardness here. Here is hardness, number 4. Number 4 in the physical properties is hardness. So I need hardness. There is a scientist called Frederick Moss. He presented a scale for hardness. By the way, this is important. It will be important just for us to know, even for our daily life. This scientist put a scale starting from 1 to 10. 1 is a very soft material. 10 is the hardest material on earth. Do you know what is the hardest rock on earth? Diamonds, yes. So we know, even as normal people, we know that rock is the hardest material. If you have a diamond ring, you can scratch with it anything. Nothing can scratch the diamond itself. So 10 is for diamond. 1 is for talc. Talc is very soft material or soft rock. So this soft rock, it has a scale of 1. This table or this presentation is very good because it gives you how to judge the hardness with something you can know. Like what? Here is gypsum number 2, calcite is number 3. But he gave you in between something called fingernail. Fingernail, the nail of your finger. If you can scratch a material with your fingernail, then the hardness is between 2 and 3. So this is good. So if I'm in the site and I have a piece of rock and I can scratch it with my finger and I see a trace for this scratch, it means that it is between 2 and 3. If I can scratch it with a copper coin, if you have a coin and you can scratch it, of course, coin is harder than your finger nail. So if you can scratch it with a copper coin, so it is between 3 and 4. If you can scratch it with a knife or the edge of a glass piece, then it is between 5 and 6. If you can scratch it with a steel tool from the side, if you get any steel tool and you can scratch it, so it is between 6 and 7. So this is very good for engineers. If I know this, then I can define the degree of hardness very easy. I have a coin, I have my fingernail, I have a knife, I have a piece of glass, I have a piece of steel, everything is available with me on site. So I can define exactly or say approximately if it is between 2, 3, 4, 5, 6, 7, this is very good. And of course I know that 10 is diamond, nothing can scratch it, so I don't need anything to check it.
Is it between 6 and 7 or just 6?
It is approximate. It is between, here, steel, it is between 6 and 7. So it may be 6, it may be 7, it may be something in between. If I say it will be in the hardest group of number 6 or the lowest group of number 7, it's on the edge, on the boundary, it's okay. It's not, for us, it's not very important. If it is 6 or 7, it's not big deal. I don't design based on hardness, but I know if you tell me I'm going to use this material as an cladding for a building, I will tell you, no, this is very soft, don't use it. It will be it will disintegrate with time. But if you use something a little bit harder, it will be better. If you tell me I will use something that is 3 or 4, 3 or 4, both are okay for me. We are not very picky to this extent as engineers. This is another presentation. This is the scale for all minerals with some presentation. This is diamond, number 10, and this is 1 talc. And in between all the other material. Starting from here, quartz is good. We may, of course, if we need to use something to drill the ground with, it should be strong. So usually our drilling tools start from, say, number 7, 8, 9, and of course 10 is for very, very soft. If I have a drilling machine and I wanted to penetrate any type of soil or any type of rock, I will use something called diamond bits. Diamond bits mean pieces of diamond all around this drilling tool so that it can smash the ground and create a hole in this ground. So this is important for us in site investigation to define the tool that is good for this type of ground. Another thing is called cleavage. Let's go back again and see where is cleavage. Here is cleavage. It's number 5 in the physical properties. It is important for us. Cleavage is the tendency of the mineral to cleave or break along a plane of weak bonding. So that's why when you look at pieces of this rock, you will find that this piece of rock sometimes is as if somebody has used a knife and divided into pieces, but actually it was naturally occurring like this. Once it broke down into these pieces with these sides. Why? Because it has a cleavage property. It means that it can break down along planes. If I give you a piece of clay, hard clay, and I tell you, just divide it into 2 pieces, you expect that you will have a boundary between these 2 pieces, but these 2 pieces are very irregular in shape. But this type of rock, when it is broken into pieces, you find that it will break down on specific weak planes. So this is cleavage. Another is called fracture. Another property is called fracture. Fracture is the same as cleavage, but rock just break, but it breaks irregularly. It does not break on a specific plane. It's defined as the way a mineral breaks other than cleavage. Cleavage is on a specific plane, but if it breaks in any other way, then it is just a fracture. That's why we say that in any rock I can see a fracture. It's not a cleavage. To say that I see a cleavage, it means that I find something straight, a straight line fracture. If I don't see a straight line fracture, it means that it is just a normal fracture. Streak. What is streak? Streak is defined as the color of the mineral in powder form. This is a mineral. What is the color of this mineral? It is dark. It is dark. It's not white. But when you put it and try to scratch the wall with it, it will leave white trace. So it means that, like tabashir, choke, if you scratch this material or change it into powder, it will change into, say, white powder. So the color of the powder of the material is called streak. Diaphanity. Another thing, but this is related to how it deals with light, how it transmits light. If it is affected with light, would it let the light pass through it? It means it is transparent. If it is opaque, it will not let any light pass. If it is in between, it is called translucent. This is important for architects. Sometimes they use material they need this material to let light pass inside the building or not to pass at all. So it is important for some types of engineers or architects, of course. There is something called specific gravity. By the way, specific gravity, we study specific gravity not as as geologists, but as an engineer. Specific gravity is something very important. What is the definition of specific gravity? It is the unit weight of material divided by the unit weight of water. It means that it will give me an indication of the density of this material. If I have a material that is very dense and I have a material that is less dense, if I divide this material by the unit weight of water and the other with the unit weight of water, the one that will give higher specific gravity, it means the density of it is high. So it is important for me to know the weight of the material. So specific gravity is a comparative tool to differentiate between the expected weight of different volumes of materials. If I have 1 meter square of a material and another meter square, meter cube of a material and another meter cube of another material, which will be heavier? The one with higher specific gravity. So this is the definition of specific gravity. How to measure it, and we will study this when we go to soil mechanics, because, as I said, specific gravity is something very important for geotechnical engineer, and we studied it. Another thing called chemical properties. Of course, chemical properties are lots of chemical properties, but what we need from here is the reaction with HCl. Why is the reaction of does rock only react with HCl? No, it reacts with many other acids and many other materials. So why I am interested in the reaction of HCl? Because it helped me as an engineer to differentiate between two types of, or two categories of rocks that are very important for me. What are these? What happens when HCl is added to a rock? If I see a reaction and I see bubbles, it means that this rock contains carbonate mineral. So this is very important. Why important? Because the presence of carbonate mineral in the soil beneath me means that this material will react in the future and may change, it may disintegrate. So if I put my building on top of a material that includes carbonates, it means with time the volume of it will diminish. So if the volume diminishes, my building will fall. So I need to check if this material contains carbonates or not. I will just, when I go to the site, I will take with me a glass bottle filled with HCl. And when I go, I just put few drops on top of the rock. If I see something as if I have boiling and a reaction bubbles coming up, it means that there is carbonates in this material. I say that no, this material cannot be used in our building. So it is important. So I'm not interested in the chemical properties itself. I'm interested in the strength of the material, but I can define the strength using the chemical properties. So I'm not studying chemical properties because I'm interested in chemistry. No, I'm interested in physical strength properties. So I can differentiate using the chemical. So I will study chemical, but I'm not going to study all of the other chemical. It's not important for me. Just the HCl reaction. I said before that there is something called mineral family. Mineral family, it helped me to differentiate between different types of rock. They have something in common. If I have few rocks that have some property in common, I can say that this is the family of this property. I will just show you something. We have just said that the reaction with HCl helped me to differentiate, to see if the presence of carbonate, there are lots of minerals that will have, or rocks that will have carbonate. So carbonates family is very important. The opposite is silicates. When I go to the site, usually when you go to the site, you will find a term. They will tell you, you have here siliceous sand. In Arabic they say raml silisi. This is very famous in sites. When they tell you that I have siliceous sand, it means that the origin of the sand is silicate. So it will not change with time. It will stay as it is all over the time. But if I have carbonates, if the sand is related to carbonates, it means that there is something called leaching of carbonates. You put your building on top of carbonate sand, and this carbonate sand, maybe after 10 or 20 or 30 years, it will react and or disintegrate, or there will be some kind of reaction and the volume will diminish. So it means that my building will be affected. So families help me to differentiate between groups of minerals that are good for my work or bad for my work. Silicates is very good, carbonates for me is not good.
How can I silicates when the chemical reactions are good?
It has no chemical reaction. Because sand usually it is either carbonates or silicates. There may be other things, but it is not important for me. But what I care for is to differentiate. I want to check, is there carbonate or not? So if I will put HCl reaction, then it means carbonates reject. No reaction, it means silicates accept. That's all. So now we have finished what we need from minerals. We are now going to go to rocks. What are rocks? We said before, rocks are the combination of more than one mineral, and it may contain also inorganic. Okay? These are the minerals, or some minerals. If these minerals combine together, they will give me these rocks. So this is quartz. Quartz is the base of granite. Feldspar, this is the base of sandstone. Mica, this is the base of gneiss. So how they change, this is what we need to study. How come I have mineral and then suddenly it is rock? It does not happen like this. It does not change suddenly. It takes millions of years to change. So I have three categories of rocks. This is very, very important for us as engineers. Igneous rocks, sedimentary rocks, and metamorphic rocks. So you have to understand this. Any engineer who does not know these three categories has a big problem in his life or in his professional life. So rocks can be classified into, as I said, sedimentary, igneous, and metamorphic. In sedimentary, the way of the sedimentation may be divided into three groups. By the way, for us it is not that important. What we need to know is that there is sedimentary, igneous, and metamorphic, and how they are formed and how they may be changed in the future. Clastic means pieces, so either the sedimentation happened in pieces sedimented together, giving me these conglomerate breccia, sandstone, siltstone, and mudstone, and shale. These are all called clastic sedimentary rock. There is chemical sedimentary rock. It means that it was sedimented. By the way, do you know what is sedimentation? What is the term sedimentation? Sedimentation means if I have, say, water with something suspension in it, and I leave it for a while, what will happen? This material that is just swimming in the water will go down. This is what we call sedimentation. Sedimentation means particles going down and reaching the bottom and gathering all together next to each other. So by the time this material changes to be rock, so it was sedimented. It was once moving with fluid or with water, and then it sedimented in a special place and changed with time to be rock. So the origin of the of the formation is sedimentation. So it is either sedimentary in a clastic form, just pieces maybe falling from top of the mountains and gathered together, or chemically, it means that there was some kind of chemical reaction that ended up having this form, or biologically, something like coal, and there is this is any rock that has that have organic origin, it's called biologic sedimentation. What about igneous? Do you know what is igneous rocks? Igneous rocks, sedimentary rocks, we said that the rocks that were formed by the sedimentation of particles and condensation together to form the rock. But igneous rock is the rock. You remember in our lecture when we said that the molten material from from below comes up as magma, the magma that is coming from below through the volcanoes, it comes outside and as lava. This lava, when it cools, it is igneous rock. So igneous rocks was once below ground, very deep below ground, and it went on top and it cooled. Once it cooled, it changed to be another type of rock. So igneous rocks are either intrusive or extrusive. What is intrusive and extrusive? Intrusive means that the cooling happened below ground. Extrusive means that the cooling happened on top of the ground. Then we have another type, which is called metamorphic rock. A metamorphic rock is just a sedimentary or igneous rock that changed with pressure and temperature to be a metamorphic rock. So a metamorphic may be foliated or non-foliated. Foliated means that it is as if it is, you know what is milfei? The milfei, we eat milfei. You know what's milfei? Milfei, gâteau. So it means that it is layers. So foliated means that it was cooled, but when it cooled, it separated into layers. Non-foliated means that no, it is not separated into layers. So as we said before, classification of sedimentary rock, it is either clastic, chemical, or organic or biological sedimentation. The clastic, like when rock weather or erosion, deposits, liquefaction, anything like this, it ends up with clastic sedimentary rock. Chemical, it means that there is a chemical reaction in this sedimentation. Organic means that there is some kind of biologic activity in this sedimentation. Let's just check here, what is this cycle? How is this cycle happening? I have rocks here on top of the mountains. It is affected with the environment, affects this. So when the environment, rains, wind, anything, so this rock starts to weather. When it weather, it breaks down into smaller pieces. This is clasts. That's why we call it, in this case, clastic rock. Clastic, it means that it is bigger pieces, it is big pieces of rock that disintegrated after weathering. So this is weathering. When this water, rain, I mean, or wind or whatever, it just move on top of the earth, it erodes anything below it. So weathering is the first thing. If I have very solid rock, nothing can happen to it. So it first starts to weather, to be small pieces, to be soft pieces, weak pieces, and then erosion start. When erosion starts, these pieces start to move, to change place, or just to be reduced in size. Then there comes a transportation. Transportation means that there should be something to carry this rock from one place to the other place. What is this? Usually it is water. The rain comes, flood comes, so it carries with it all the weathered, eroded material. It carries this material with it within the flood. If you see any flood, you will find on top of the flood lots of things. You may find cars on top of this flood. So if it can carry cars, it will carry just disintegrated and eroded pieces of rock. It will transport this material from one place to another place. Then it comes a deposition phase. What is a deposition? This material is swimming or carried inside water. It will not be carried all of the time. When the velocity of water starts to decrease, the bigger material starts to fall down, and the smaller material will start to be carried, and then it will be carried more with water till the velocity decreases again. Then the a little bit smaller material will fall down, and so on till we go to the end. By the way, this happens in the delta. You know what is the what is the delta of any river? Delta, in the delta of the river Nile. What do we say about this delta? That it is very fertile and it is very good for cultivation. Why? Because it does not contain any big pieces. It is just clay, fine material. So why? Because this material came from Ethiopia and from Sudan and from very long distances away. It came with flood, but small parts. So the big parts fall during the trip, but the last material that was deposited is in the delta. That's why the delta consists of very good land for cultivation. You cannot find pieces of rocks in the delta. No, it is only clay, which is the finest material. So that's why when deposition happens, by the way, this will show you, this is the water coming full of material. At this location, the velocity is a little bit high. So only big material will be settle down. Then later the velocity will decrease. So medium grains will settle. Then when I go here will be the delta. When I come here, the water is very, very slow, and it may be a little bit, it may reach to be stagnant. When this happens, all of the fine particles settle down, and this is the formation of the delta. So then this is the deposition phase. The last phase is lithification phase. The material is now deposited, but they are loose. They are just next to each other. They are not rock. So something should happen so that this material would stick together to each other. How come this happens? It happens either cementation or compaction. If I just put a material in between, and this material works like a glue, it will join the pieces together. But if I just put pressure and temperature, they may be in one piece, like when you bake a cake. You put some ingredients and you put it in the oven, you get one material, just one material. It's a cake. So how this happened? Because of heat, very high heat. So here we have heat, pressure, it changes to be good rock. This is what is lithification. We said that it's either cementation or compaction. Let's see how cementations happen. This is the material. These are the pieces of rock under the microscope. If a cement or some kind of material that acts like a glue fills the spaces inside, it will combine material together. Compaction is just pushing the material next to each other, adding temperature, so they solidify together as one piece. These are examples for what we said. You know what is sand dunes? كثبان الرملية. if any one of you see a sand dune, you'll find that it is a very loose type of sand. If you just blow some air, it will move. So very, very light. This material can be changed into hard sandstone rock. How come this happened? With time. This material, if it stays in place and is subjected to pressure and very high heat, it changes to be rock. But it takes millions of years to do this. And later, after another million of years, maybe it would disintegrate again and change to be sand again. So that's why usually when I study rock, I always tell you what is the origin of rock. If I tell you what is the origin of sandstone, you will tell me the origin of sandstone is sand. It may be fine sand, medium sand, big sand, it depends on the type of sand. But the origin of sandstone is sand. And when sandstone disintegrates, it returns back to sand. So this is the process of cementation. The other type of rock, this is very, very important in site investigation, to know igneous rock. Why? Because igneous rock as a rock is hard. You think with me with this problem. Igneous rock is rock, but it is formed on top of the ground or maybe within the ground. If I make a site investigation and I find rock and I say, okay, I reached the bedrock, this is a very good layer. Then later I discover that it was a thin layer, but it is followed by another very soft material because it just came from below and the eruption of the volcano just throw it on top of the ground. It does not mean what is below is good. So this is important for me to define igneous rock. So in igneous rock, this is textural classification. How it is, for igneous rock, you have few things that you need to classify. The way it was cooled, did it cool quickly or cool slowly? I said that it originates from the very hot magma below. So, did it come on top of the ground? If it came through the volcano on top of the ground, then it will cool quickly because suddenly it was a few thousand degrees and suddenly it was affected by 0 degrees centigrade on top of the ground. So this will be a quick cooling. But if it cools below the ground, then it will take longer time. So the way of cooling is important. Why it is important? Because when something cools slowly, the grains are big and it will be stronger. But when something cools rapidly, the grains will be fine and it will be softer than the other. So this is important for me. That's why they tell you here, gabbro, diorite, granite. We all know that granite is granite. This is a very strong material. You know, when the pharaohs, they have statues made of granite, we say that how come that they managed to carve in this material? This is very strong rock. So coarse grained are very strong. Fine grained are less strong. They are still rock, but they are less strong. Here, this is important for you to define, because you may be asked in that, what is the difference between magma and lava? Definition. What is the difference between magma and lava? They both originate from the solid material. Magma is below. Magma is the material below. When it comes on top of the earth, it is lava. So what is coming out of the volcano is called lava. But maybe a few seconds ago, it was magma. This is a presentation for the grains of the soil and how strong is it. Coarse-grained, fine-grained, and which is strong and which, of course, coarse-grained are stronger. Granite, diorite, gabbro, these are strong rocks. Fine-grained, rhyolite, and andesite, basalt are less strong. So this is, there is a term called felsic igneous rocks and mafic igneous rock. So felsic igneous rocks are relatively rich in silica. Mafic are richer in magnesium and iron. Of course, for me, I don't care if it is silica or magnesium, but what I care for is the properties of this material. If silica is good, then for me, felsic would be good. If magnesium and iron are important, then I need a mafic type of igneous rock. This again is an illustration for the difference between extrusive and intrusive igneous rock. This is the volcano, this is here is the magma, here is the lava. So here the intrusive igneous rock, extrusive igneous rock is cooled on top of the ground, intrusive is cooled below the ground. The crystals here are very big compared to these crystals of the material on top. Of course, this is stronger than this. Imagine here as a geotechnical engineer, when we speak about strong rock, I don't care for is it lava or not lava. I care for the material. When it is extrusive, then it means that it was cooled on top of the ground. It is, the name of it is lava. So it will be weaker than the intrusive, which is below. But still, both of them, I'm not sure that this is, I can call it magma. Magma is here, the below here is magma. But when it went outside, it cooled here. Don't call it anything, but here it is lava. Here it is something in between. You can call it lava that cooled below the ground or magma that went a little bit on the top to be cooled. So, but what I care for here is the differentiation between extrusive and intrusive. As a geotechnical engineer, imagine that you want to put your building here and you made a site investigation. When you do a site investigation, you are going to drill boreholes. Once you drill the boreholes here, you will find that you touched the rock. Okay, I'm fine. I reached the rock. I will stop. This is good land. I reached the bedrock. But actually, is this the bedrock? No, it's not the bedrock. It is just a piece of magma that came from outside and just cooled at this level. If I penetrate with the borehole deeper, I will reach, maybe this is a very soft soil. It's not important. If I'm standing on a big piece of rock, then it is solid. But if below this piece of rock, I have 1 meter of sponge, is it important? Standing on a very big piece of rock on top of 1 meter of sponge, is this a solid foundation? No, it is not a solid foundation. That's why it is important. That's why we are now concentrating on what is important for us as engineers, especially as geotechnical engineers. If I do a site investigation and I reach rock, then I have to define the type of the rock. Is this rock igneous or sedimentary or metamorphic? If it is igneous, it is not enough for me to stop. I have to penetrate deeper. I may go maybe 10 meters in igneous rock just to prove that the igneous rock will continue a very big distance. But if it is just a thin layer, 1 or 2 meters, I cannot just take 1 or 2 meters in igneous rock and stop. No, maybe it is followed by very soft sand below or very soft clay. This is a very good presentation. This is here the magma chamber. If you want to differentiate between the lava and the magma, this is the magma. Here, this is the lava outside. So outside, this is the lava. Here, it is the magma. Anything in between is part of this magma that cooled. If it cooled here, it is still within the soil. If it cools outside, then it will cool very quickly. But I have here a definition, 2 other definitions that you have to know. Batholith and laccolith. Batholith is this. It's the magma chamber. It is the magma below. Laccolith, it is just a piece of the magma that is cooled here. It cools like in a lens form. It's another way of differentiation other than intrusive and extrusive. They are more or less the same. This is extrusive, this is intrusive. So this is intrusive. So laccolith is intrusive, but this is extrusive. But what is the difference between this and this? They are all in. This is intrusive and this is intrusive. But this is intrusive laccolith and this is intrusive batholith. So that's why sometimes adding a figure, I also advise you add this figure to your list of terms because it combines many things together. So this is batholith, this is laccolith, this is the lava, this is the magma. Anything from this magma chamber that fills any crack, inclined plane crack is called dike. But if it fills a horizontal crack, it is called sill. This sill is just the magma filling a horizontal crack. If the magma fills a big lens, it is a laccolith. But if it fills just a crack, it is called a sill. As I told you from the beginning, geology, you have lots of terms. If I tell you differentiate between laccolith and sill, the only difference between them will be the thickness. That this is more or less a lens, but this is just a crack filled with this material. The third type is called the metamorphic rock. Metamorphic rock. Okay, so we will just pause our lecture here to stop this video and continue with the next one just after.